How Lime Mortar Works. That's an ambitious title, isn't it? Over the next 20 minutes, I intend to do this humble, understated wonder material some justice here. As a quick overview of the presentation, I'm going to break the question of how it works into three constituent parts. Part 1, structural behaviour. You're going to hear from a structural engineer why strength of the mortar doesn't really matter. Part 2, weatherproofing behaviour. We're going to look at how lime mortar grapples with moisture in masonry buildings and examine breathability of old buildings as a process. Part 3, sacrificiality. Now this is the part that requires the fresh coffee, and we're going to probe the sort of holy grail aspect of masonry conservation, the sacrificial weathering phenomenon. Now, understanding how it works is all good and well, but it's a bit of an academic point unless we can bring that knowledge to bear in a specification context. So then we're going to have a quick point towards, look, how can we specify our mortars today with the knowledge that we're replicating the functionality we see in historic limes. Then we're going to sum up and move into the Q&A session at the end. Structural behaviour. I want to debunk a couple of myths along the way. So myth number 1, the mortars need to be strong. Okay, engineers, I am aware, get a bad name for this in the conservation business. Now, I want to draw the distinction between the structural behaviour of old buildings and new buildings. Old buildings draw strength and stability from their shape and mass. So in response to destabilising forces, it's just their weight arranged into a stable form that's keeping them standing up. Okay, so the internal forces are all compression based. No tension, no flexural stress. Distinction with modern masonry buildings, essentially the walls work like thin reinforced concrete slabs on their side. So in response to destabilising forces, they need to develop tension across the mortar joints to create flexural resistance. Okay, so the role of the mortar joint is totally different from old buildings to new buildings. Old buildings just to keep the bricks apart, whereas in new buildings it's to stick the bricks together. Okay, so big distinction in the role of the mortar joint. So if it's not sticking the bricks together, which is absolutely not, it's just a load bearing spacer between the stone units to prevent them from point contacting one another and splitting. Okay, now traditional lime mortar, spectacularly weak, of the order of 1 to 2 Newton per square millimetre. That's for our friends across the pond, that's somewhere between 150 and 300 psi. Okay, so low strength, which sort of invites the question, with such low strength mortars, how are our old buildings standing up? Now, when you look at the strength curves for the code of practice for load bearing masonry, you'll find that for a weak mortar, you can get very strong masonry as an overall assemblage. And the sort of the wee pink one is what I've idealised for what a traditional hot mixed lime mortar might be. Now, you'll find that for very weak mortar, you get ample strength out of your masonry, and you're thinking, like, where does this come from? So when you look at the stress transmission between across the mortar joints, you're thinking, okay, well, if my mortar's only good for 1 Newton per square millimetre and I load it up with 5, why doesn't the mortar just squash out the joint? It's a silly question, but it's got a complex answer. Now, it pays to look at how the strength of masonry is measured. So if you cast a cube of mortar and load it up in a crushing rig, as it approaches its ultimate strength, it tears itself into vertical strips. And those vertical strips are wee side-by-side columns that then buckle. And when they buckle, it collapses. And that's the ultimate strength reached. Stone masonry units, similar process, but it's significantly higher strength. You're talking a clear order of magnitude between mortar and masonry unit. So, but it's a bit more complex than just the dilution of a weak material with a strong material. Like I said, the stress transmission through the joints, you're thinking, where does this go? Well, when you actually build mortar into masonry, the actual mortar strength in practice significantly increases, because with each masonry unit becomes, it laterally binds or clamps together the head of those wee columns that are trying to form, so they can't buckle. So the mortar is actually in a state of triaxial compression and can support significantly higher strength. So you can get very high strength masonry out of very low strength mortar. Okay, now, but is that high strength actually required? Well, Gothic cathedrals are about as far as you can push load-bearing masonry as a structural material, and still, even in the highly loaded members like crossing piers, you're talking stress, like mean compressive stress, very low, of the order of round about 1-2 Newton per square millimetre. So high load, low stress, thanks to the massive section area. Now, so you can get high strength masonry out of low strength mortar, but as we've seen, high load, low stress, thanks to the massive section area, strength still isn't that important. So it was a bit of a red herring to make the point. Okay, what is important about the structural behaviour of the mortar joints is its deformability. So that's the deformation modulus. So the mortar is essentially a deformable cushion to allow the stonemasonry units to shuffle about to cope with nothing short of wanton destruction to the foundations. If you ever get the chance to visit our island, go to Carlisle Cathedral. It's an engineering playground for how arches work, and you can see the role of the mortar is essentially a deformable filler to keep the stones apart so that they can shuffle around to a stable form. So from a structural engineering perspective, structural masonry is Lego bricks bedded in plasticine. So strength's not really that important. That's me, an engineering pariah now. The cat's out the bag, and I will be looking for new employment sometime soon. So a quick recap on the structural behaviour. So traditional masonry, high load, low stress, stress so low, strength, bit of a red herring, and we're looking at Lego bricks jointed in plasticine from a structural behaviour perspective. Okay, weatherproof behaviour. So another myth that I want to debunk is that old buildings breathe by vapour permeability of the walling fabric. Vapour permeability, terrible way of describing how old buildings breathe. I'll come back to this. So the small business of keeping the water out. Now, I can only speak for us here, but as you might imagine, I'm from the west coast of Scotland. That's the dark blue bit there. Walls get wet you're talking of the order of tens of tons of water every year is incident on our masonry building walls. So that's a lot of water, and it's got to go somewhere. Now, the walling fabric is essentially an absorbent buffer between inner and outer environments. So that's a thick mop to absorb, store, and recharge the water out to the external environment when conditions permit. It's that recharging cycle that I'm interested in here. So I'm going to deal with two contexts. So context A, we've got non-porous stone masonry, so granite rubble wall, bedded in traditional lime mortar. In context B, similar stone rubble wall, but with porous masonry units, so sandstone for talking sake. Okay. Now, before we look at how moisture moves through masonry fabric, it pays to look at the spontaneous natural water distribution in a porous material without movement. So what you've got on the left is an idealised random cross-section for a porous material. The grey bit is the solid phase, the white bit is the pore, and the blue bit is the water. Now, some physical principles. Water molecules adhere to the walls of wettable solid surfaces. Okay, so that's like little magnetic marbles sticking to the wall of the pores. Now, if those marbles also were attracted together, then you're looking at water molecules, so they're self-coherent, they're attracted to one another as well. Those two physical principles compete, and if you chuck a bucket of water on a block of dry sandstone, you'll find that the water tries to wet as much internal surface area as it can, so that's adhesion, whilst maintaining intermolecular connectivity, so cohesion. The outworking of that is it creates a film across the pore walls. At high moisture contents, that's a thick film. At low moisture contents, it's a thin film, but it tries to stay interconnected. Introduce a drying front to this and watch what happens. So the principal driver behind the drying of wet stuff is wind blowing across the surface. Okay, so wind blowing across the surface physically removes water molecules from the front of the material. That opens up a bit of free space of wettable solid surface. The next magnetic marble in the queue bumps forward to stick to that, but because he's coherent to his pal behind him, he bumps forward as well, sticking to him, and the whole chain of marbles starts to roll through the material towards the drying front. That's capillary drying, okay, non-saturated capillary flow towards a drying front. In other words, you take a wet sponge and blow a cooled hairdryer across the surface of it, you'll find the whole sponge dries out, not just the surface, and that's because you get capillary flow through the material. When you look at lime mortar on a powerful enough microscope, it looks suspiciously like a sponge. So essentially you've got a load-bearing structural sponge built into the wall with a cold hairdryer blowing across the outer surface. That's what's happening. Non-saturated capillary flow, convective drying. Now, the wall gets wet according to its total area, but it can only dry in this context according to the total surface area of the lime mortar joint. So the lime mortar has to work hard, so it needs to be thick enough to store all that water, and then work hard to recharge that water out to the external environment. Scenario B, a sandstone wall with a good lime harling. So you've now levelled the playing field between the propensity of the wall to get wet and its ability to dry back out. So significantly enhanced the drying capability. But there's more going on there, so we'll probe poultice mechanics in a wee minute. But essentially, a fine poured material will soak water out of a coarse poured material into itself. So that's like drawing the body of water out of the coarse pores into itself, closer towards the drying front. It also keeps the coarse poured material drier for longer. If you cover a coarse poured material with a fine poured material, the fine poured material is the one that's getting wet, and it doesn't want to let go of the water into the coarse poured material by those same poultice mechanics. So it's right at the front of the material when the wind keeps blowing but the rain stops, ready to dry back out. So harling, prime culmination of poultice principles is key. Now, this weatherproofing business is intimately tied to its ability to deform. So the mechanical characteristics and the weatherproofing characteristics intimately linked. Okay, so you need to maintain capillary continuity between your stones and your mortar and throughout the body of mortar for all this business to work properly. You do not want a brittle material in your between your stones, because that will snap and create airspace, which massively impinges the water movement through the material. Now, you'll notice this is all a water movement process, liquid phase. It's not a vapor phase process at all. Now, the business of vapor permeability is an absolute nonsense. It's a terrible way of describing how old buildings breathe. Old buildings breathe by convective drying. So the proof test of this is if you take your wet clothes out the washing machine, hang them up on the washing line, and for academic purposes decided to erect a Gore-Tex tent around them, what would you find? Well, Gore-Tex, fantastic material for hill walking and so on and so forth, waterproof, but it's windproof. And whilst it's highly vapor permeable, because it's windproof, it starves the wet material of access to the favourable evaporation conditions, i.e. inhibits the wind flow blowing across the surface. So lo and behold, wet clothes. Any backpacker knows that it's really difficult to get your wet kit to dry on the inside of a tent. Okay, so quick recap on weatherproofing behaviour. So solid wall, just an absorbent buffer. It's a holding tank, a spongy mop to soak up, hold and recharge the water out. And it does this in a convective drying capillary flow, not vapor permeability. Okay, harling being the prime culmination of that process. Okay, sacrificiality. Now, this is the masonry conservation holy grail. Now, another myth I want to debunk here is that heavily hydraulic binders are compatible with traditional masonry. Okay, so lime mortar is grappling with moisture, the ending of decay, but how does it preserve the stone masonry units? Now, in the UK, principal agent of decay is salt attack, not frost attack. Now, salts are harmless in solution, but when the body of water that the salt's dissolved in then evaporates is where it causes its damage. So the salt ions crystallise and create wee needles, like wee spears, stabbing the pore walls, breaking down that mineral binder into essentially turning an engineering strength sandstone into mush you can poke your finger into. So it's a big problem. Now, the SPAB had a key insight into this. That's the Society for the Protection of Ancient Buildings. Key Insight in 1979 published their findings on observations of masonry structures as they dried after periods of wind-driven rain. They noticed that the lime mortar joints appeared to soak the water out of the masonry units and into the lime joints. where the bulk of evaporation took place, and then lo and behold, that's where the salt crystals were deposited. The Eureka light bulb went on, penny dropped, and this was dubbed sacrificial weathering phenomenon. How does this work? Okay, so when you've got two porous materials of distinctly different pore size in intimate contact with one another and chuck a bucket of water on that, you have a poultice. So water preferentially drawn out of coarse pores into fine pores by those same capillary mechanics we've seen earlier on. Okay, now, and with the moving water come the soluble salts, and this is mobilised by wetting and drying cycles, and we get those several times a day in the west coast of Scotland. And over the lengthy lifetimes of masonry structures, you get an incredibly pronounced salt management process. So I've shown the what's going on in the mortar joint around the arises of the stone in the spirit of how the SPAB published their findings. So when you take a microstructural examination of both the materials and see the relative pore sizes, you can explain why there's a water management and implicitly a salt management process at work here. So poultice mechanics is at the heart of the sacrificial weathering phenomenon. So we've seen this photo at the front. So that's a bit of sandstone masonry walling with traditional lime mortar joints, and you've got soluble salt caked on the surface of the lime joint and nothing on the surface of the stone. This is sacrificial weathering caught in the act. Okay, so and if that much was true for the bedding joints, well, how much more true would it be if you just extrapolated that across the full surface area? So traditional lime coating, prime culmination of poultice mechanics. And it's plain to see just the drying out capability of a good lime Harlan versus some nasty cement that we've been inflicting on our cultural heritage for the last century. Now, the reverse weathering process is why cements and other modern materials cause such damage. The salt, the evaporation is forced into the stonemasonry unit where the salts then are deposited and you can turn it into mush. Okay, we've seen this at Glasgow Cathedral. What you've got here is a pore-sized distribution spectrum, again, of three materials in this wall. So you've got your sandstone on the left, that's your coarse pored unit. You've got your traditional lime mortar from the back of the bedding joint, that's your fine pore, and you can see there's a distinct difference in pore size, so it's a very effective poultice for pulling the water out of the stone into the lime. With the moving water go the soluble salts, but that's plugged with a very, very nasty cement mortar. Now, you'd think, okay, the cement, okay, it's again smaller in pore size than the lime. Why doesn't it just pull the water into the cement? Well, the capillary flow only occurs down to a certain pore size. By the time you get beneath 200 nanometer in pore size, capillary flow grinds to a halt, and that porosity is completely ineffective for water transport purposes. So rather than being a poultice, it's just a plug holding the water in the joint. So what you can see, the mechanics of the drying behaviour around the joint there, shown at the bottom, the fine poured bedding mortar soaking the water out of the stone, but it's got to evaporate through the stone arises to get around that plug, and that's why your arises are weathering preferentially relative to your bedding, relative to the surface of the stone. Okay. So, quick recap on sacrificiality. So, sacrificial behaviour of the lime mortar is just a direct outworking of its weatherproofing behaviour. The water management of the mortar is an outworking of its microstructure, and with that moving water come the soluble salts. Okay. Now, how can we replicate this process? So when you look at lime mortar on a fine enough scale, it is essentially a sponge, a coral reef looking thing through a powerful enough microscope. That's a sponge soaking up that water and drawing it out the wall, and with the moving water come the soluble salt. What creates that sponge? Well, when you look at it through an EDX microscope and identify the minerals at work here, what you're looking at is calcite, that's carbonated free lime, in the mortar mix to create this optimal spongy microstructure. And we need to be replicating this mineralogy of our binder if we're going to create that sponge in our mortars today. So we need to do this by targeting an air or a an air lime or a feebly hydraulic lime to create that calcium carbonate, which creates that sponge. I don't have time to go into the difference today, but there's a big distinction between your authentic traditional hot mix lime mortar you see on the left from Balvenie Castle. It's fine poured, the pore size distribution centred around that 1 micron pore size. So you set that next to a coarse poured masonry unit, and it's clearly a very effective poultice, very effective for capillary drying. So it's doing all that moisture management and your sacrificiality business, and so that's the ideal blueprint. Whereas compare this with an NHL, lower porosity, but the pore size of that porosity is the problem. So it's largely ineffective for capillary transport processes and is not as effective a poultice. So big distinction between traditional lime mortar and NHLs. So we need to be starting with quicklime as a base, using a lime-rich binder type, so that's quicklime, non or feebly hydraulic in binder type, and then use it in traditional binder amount. So binder type and binder amount issues, okay? And you can look at some sample specification types to at pleasure. Okay, so to sum up, we broke down how lime mortar works into 3 constituent parts. Part 1, structural behaviour. Strength, a bit of a red herring. It's deformability that's the key. Part 2, weatherproofing behaviour. We looked at how lime mortar grapples with the moisture, and that is a convective drying process. Liquid phase, vapour permeability was a nonsense. And sacrificiality is a direct outworking of that behaviour. And we see that the lime mortar is essentially a permanent poultice that's built into the wall. And we've seen that this is best replicated in practice by us specifying an air hot mix lime mortar, or non to feebly hydraulic if we need it. Okay, now thanks for your attention. That's all from me just now. We'll now move into the Q&A session.